In section 12.6, we analyze damped oscillations. Our objectives here are to account for the resistive forces and the transfer of mechanical energy in a damped oscillator, and use this to solve some problems. We also want to explain the various types of damped oscillations. Now, realistically, there are resistive forces in nature. There's friction, there's air resistance, and up to this point, we have not worked with any of those things on our oscillators that we've been studying. Realistically, a pendulum is going to encounter some air resistance, or you might have something like the block on a spring, but that block on a spring oscillating through maybe some type of liquid, like putting it into a glass of water. Now, what I want you to recognize is that if that's the case, if you have this resistive force that's going to be acting against you, your mechanical energy is going to diminish. And that's what we call a damped oscillator, or damped oscillations. Now consider an object moving through a medium. Maybe it is this block on a spring that's moving through a glass of water. There's going to be some sort of fluid friction that's involved there. And we've already studied resistive forces. We know that the resistive force is proportional to the velocity of the object through that medium and in a direction opposite the motion. We know that R is equal to negative BV. So if we were to sum up all of the forces acting on this block, we would have that restoring force of the negative kx from the spring pulling on it, and we would also have this negative BV that would be acting on it that we could set equal to MA. Now, using our knowledge of calculus, we could rewrite the V as a dx dt, and we could rewrite the A as a second derivative of position with respect to time. Now, this is another differential equation, and we're not going to go through the proof of where it comes from, but I simply need you to know that the solution to this differential equation is this monster right here, where now we have an equation for the position x of this oscillator at any time as it bounces up and down inside of this liquid, and its position is equal to a e to the negative b over 2m times t times the cosine of omega t plus phi. Now, some things to know. B is, of course, this constant here of that resistive force. A is still a maximum amplitude that you're starting at. E is that same e to the x function that you already know about. M would be the mass of the oscillator. T would be time in this case. Now, what that means is that when we look at our equation for the position of the oscillator, that this portion of the equation out in parentheses here is actually dependent on time, which means that the amplitude of the motion is dependent on time. And that's why we see this graph down here, where you start out at some maximum amplitude here, but we notice that as time goes on, that amplitude diminishes and becomes smaller and smaller and smaller as time goes on. This is what a damped oscillator would look like, a changing amplitude that gets smaller and smaller as it is being damped. Here we could also say that the omega for this oscillation and that oscillatory motion that's taking place there is equal to a square root of k over m minus b over 2m, that quantity squared. So we have, again, our omega values that we could plug into the equations as well and solve for this oscillatory nature of that, or that angular frequency. Now let's talk about different types of damped oscillators. There is what we call the underdamped oscillator. That's when the resistive force is relatively small and the oscillatory character of the motion is still preserved, but the amplitude of the vibration decreases and the motion ultimately ceases. That's basically what I just showed you, where you start out with some maximum amplitude, but that amplitude decreases over time and ultimately is going to sort of stop eventually, like the block oscillating through the water. Now, another way to express angular frequency for that damped motion, remember we had the square root of k over m minus the b over 2m squared. We could rewrite that square root of k over m as an omega naught. Omega naught really represents the angular frequency of the oscillation in the absence of any sort of resistive force. So what the omega would be if there wasn't any forces resisting that motion, any sort of friction or air resistance. Now we could define an undamped oscillator, which is basically when B equals 0. And if B equals 0, this whole term equals 0, and omega simply equals omega naught, which basically says this object is going to oscillate at what we would call the natural frequency without any resistive force. But if B grew and was no longer 0, your resistive force is going to grow and your oscillations will begin to dampen more quickly. There's also something called the critically damped oscillator. This is when B equals a critical value of B such that B over 2m actually equals omega naught. And if that's true, and this equals omega naught right here, then this entire term turns out to be a 0, ultimately meaning that there is no angular frequency. And if there is no angular frequency, then this object is not going to oscillate at all. And instead, what we're going to see is this critically damped nature where it just quickly returns to its equilibrium position. You pull it out to some amplitude here, it does not oscillate, but instead very quickly returns to equilibrium. Another one that we could look at would be what we call the overdamped oscillator. An overdamped oscillator is one where the medium is very highly viscous. Think about putting that block on a spring into a vat of honey or something that would be really thick like that. And in this case, for an overdamped oscillator, B over 2m is actually greater than omega naught. Notice that if B over 2m is greater than omega naught, then this term is the larger term, meaning that we end up with a negative under the square root sign, or an imaginary number. So again, omega does not exist. There is not going to be any oscillation in this type of motion. But instead, we have the thing being pulled out to some amplitude A and very, very, very slowly returning to its equilibrium position. So no oscillation in this case, but instead very slowly just simply returning to equilibrium. Now in each case, your mechanical energy is eventually going to fall to 0 as that energy is transformed to internal energy in the system and in the medium in which it is oscillating.